And this part's going to get a little bit hard, so Dana had the timing just right to put me on the spot. So
don't scare them in advance.
All right, so we're going to be using some mathematics and some ideas from topology. Okay, you know, what is topology? You've maybe heard jokes about coffee mugs being the same as donuts. Okay, that's what we're talking about with this topology business. And it turns out that donuts and coffee mugs have something to do with the lambda-calculus. And correct me if I'm wrong, Dana, but I think that idea is due to you, that there's some similarities there.
Well, I'll explain a bit of the history thing because it should have been obvious earlier because people were doing things. So I'll explain it in a slide halfway through there.
Okay, very good. Very good. So, so we all, you know, use abstraction a lot, you know, to take a lot of common things and then be able to talk about them in one fell swoop. And topology is a kind of abstraction like that, okay? And perhaps one of the main examples that you'll want to keep in your head from school is something like the real numbers, okay? So we're all familiar with the real number line, okay? All right, we've got our real numbers. And so this real number line is an example of a topological space, okay? And you've got points in the space, and that literally corresponds to, you know, points on the number line, okay? And then what's going to happen, and there's lots of other examples of spaces out there, and one of them is going to be the notion of function, actually, that we've got in the lambda calculus. And so you could imagine, you know, some I don't know, cloud of all the functions out there. And then there might be a particular function, like let's say the factorial function might be one of those functions in that space of all functions, okay? Okay, so that's just kind of situating where you're at. Now, the interesting thing about why topology has something to do with functions in lambda calculus is that in both scenarios, there can be this interesting interplay between finite things and infinite things, okay? And infinite, in the real numbers, I'm going to focus on like by infinitesimal, like things that are hard to describe finitely. So, but first, let's say you just have something like, I don't know, a fraction like 2/3. That's super easy to, you know, these rational numbers are super easy to describe, you know, very concisely and finitely. But what about irrational numbers like square root of 2? I mean, obviously the symbol square root of 2 is a nice finite representation, but if I wanted to know exactly where to put it on the number line, that might take a while to figure out exactly where it goes and so on. And so there's a notion of infinity going on there. And then with functions, if you think about the factorial function, if you think about the mapping of numbers, right, that if you were to try to tabulate what the factorial function does, you know, you've got like 1 goes to 1, 2 goes to 2, 3 goes to 6, you know, and I could try to tabulate the whole thing, but it'd take me a long time, wouldn't it? In fact, it would just keep going forever, this giant table, right? And so there's also a notion of, so in some sense, to accurately sort of pinpoint that point, it would need, you know, in a very explicit way, you'd have to have this infinite table to do it. Okay, so infinite is there in both scenarios. Okay, so let's get into this notion of what's similar going on here and what draws these two things together. And so we're going to introduce the notion of a base. Okay, and you can think of a base. There's lots of different things that could work, but in the real number scenario, one nice choice of base would be like maybe take a rational number with a sort of a plus or minus error term around it. Okay, so you get an interval. Okay, and you can think of this interval as being an approximation for a real number, right? Let's say you're trying to measure some particular real number, but your instrument is only good plus or minus a certain error a bar, okay? And the real thing might be anywhere in that interval, okay? So that's one example of a base. So you could take this neighborhood. Each of these intervals is a neighborhood, and then the base is just all of those neighborhoods, okay? Now, what's the similar idea for functions? Okay, I'm maybe getting a little bit ahead of myself here. I'm going to pop forward and backward a little bit.
Yes, you're getting ahead of yourself.
Maybe I won't talk about functions yet. I will leave it to a few slides to talk about functions.
One thing you should ask: how many neighborhoods did you need? How many neighborhoods did you need?
To talk about the whole space, the real line. Anyone? So you need infinite many. Yeah.
But how many?
Can you there's different kinds of infinity, right?
That's what's my question.
Are they countable?
Because if you're going to think of decimal approximations, so the decimal approximations, each cutoff is rational. And what's left over is littler and littler. So you really only need intervals which are centered at a rational number.
Right, just like I did here.
Rational amount of play on either side there. Because anytime you want to get close to a number, you can always get there, and with any set closeness, you can find it there. So you only need countably many, because you only need rational spheres at rational points. That works in all Euclidean spaces. Just use rational balls with rational radii. And that's enough to get close.
As close as you ever want to. Or need to, in your lifetime.
But that's more the computational kind of point of view. Mm-hmm. And so the other thing is about using open sets. So what's the connection between neighborhoods and open sets? And why should we bring that up?
Right, and so so your neighborhoods that you should be able to essentially create an open set by taking a union of a bunch of neighborhoods. So you can sort of describe any open set on the real line, so any interval, even one that sort of maybe, let's say we want to talk about this is the perfect example. Let's say we want to talk about this open set where the endpoint is on the square root of 2. Okay, that's not a rational, right? But could we still describe this interval with just a whole bunch of these rational intervals? And the answer is yes.
Why?
We can take basically all the intervals that are decimal approximations of the square root of 2
Yeah.
as one of the endpoints.
Right.
But it may be that you have to get closer and closer and closer till you're inside the irrational interval, right? See, if you take an irrational interval and you look at one point in there, if you're very careful with that calculation, you can make your rational interval small enough to be entirely inside.
Mm-hmm.
So that's what you have to be careful of. Mm-hmm. And in speaking about these open sets, with an interval, don't include the endpoints, right?
Yeah.
Only include the interior points.
It's an open interval.
Yeah.
Square root 2 not.
Yeah, and that's these curly, or the using these curved ones is the notation for open intervals. Yeah. So it does not include the endpoints. Yeah.
So you're saying an interval that ends at square root of 2, meaning there's no number greater than square root of 2 but less than that interval.
Yes. Yes. So everything greater than square root of 2 is in this interval.
And you're saying that's possible with rational.
We can approximate this interval. It takes an infinite number of these. We can take the union of an infinite number of these kinds of
Countably?
yeah, and we can use them to sort of get closer and closer and closer to square root of 2. We never actually get there, but that's okay, because if you were to pick, let's say you were to pick some particular number that was super close to square root of 2, keep going down, down, down with our rational, we'll eventually get to a point where we cover that point.
I have another good example here of the difference between neighborhoods and open sets. Let's take a two-dimensional plane, and let's think of the unit square there without the boundary. To make it open, it should be without the boundary. Now I said we were supposed to topologize the Euclidean spaces by means of spheres. Now a sphere is just a disk around the center like that, without the boundary to be an open.
So that's his neighborhood, is that sphere.
That's a neighborhood of that point, but it's also a neighborhood of that point too, or that point there, as long as the point is inside there. So, is it obvious that an open square can be filled with open balloons? Think of it maybe in 3 dimensions. Can you fill up a square cube with circular balloons? It's just that when you get over around here, you have to make them awfully tiny.
That's the trick. You have to have balloons that can go infinitely small.
Anyway, the open sets are the ones that are unions of families of neighborhoods. There may be an awful lot of trouble to find that family, but still, it's what it needed to show that the thing is open. There's a question about that.
Yeah, so countable is still infinite.
Yes.
It's just like a lower order infinite.
Yeah, countable just means that you can line them up with the natural numbers.
Okay.
But the natural numbers are infinite, so.
And then on the neighborhood, is that kind of like an equivalence class?
Yes. Yes.
Is it an equivalence class, or it's
well,
kind of like
one? I mean, a neighborhood, it's saying everything inside of here is in the neighborhood.
Okay, maybe if you take the center of the circle there, you can say, I'm thinking the things that are fairly equivalent to the center there.
Yeah.
They may be off-centered,
Yeah.
but they're sort of equivalent.
Yeah.
But I don't think it's an equivalence relation that you use for very long, because we're just looking at one approximation here of how you put a neighborhood around the point.
Yeah. I think they're.
Neighborhoods have to be centered on it, or can they be like off-centered?
Yeah, they don't have to be centered. That's just one way of doing it. Yeah. Yeah.
So the reason for having the centers is if you want to count them, you take a rational center and a rational radius. But that sphere is a neighborhood of all the points inside the sphere,
Yep.
which are not at the center.
Yeah. And maybe to go a little bit further with why is it that they're countably infinite? So you need those 4 numbers to encode your rational number and its epsilon, the rational plus or minus. So that's 4 numbers. Well, with Gödel encoding, you can take those 4 numbers and turn them into 1 number, right? And
That's how
then,
you count everything.
yeah, and so that's the number that it appears as you're counting would be that number, right? All right, was there another hand up over this way, or?
Another way of looking at it, so you have countably finite number of decimal places, and each approximation can go to one of those.
Right. Yeah. And then each approximation, of course, there's a lot of real numbers that one might be trying to describe. All of the ones in the circle or in the interval. Okay. Was there I remember there are.
I think I understand the open set and neighborhood, but what's the base?
A base is just saying we're gonna be using sort of neighborhoods of a certain shape or form to describe the whole space. So here we were sort of saying, oh, we're only going to use disks to describe the space, right? So the base is sort of that decision to say we're going to use disks. Okay, so mathematically it is just a big set of these neighborhoods.
Why is it finite? Why is there a finite intersection of finite intersections? Why is it finite?
This one here.
Both of them, and
Okay, see, the thing is, we're familiar with many different setups, so also to answer the question, we could have taken a base for Euclidean space cubes, right, instead of balloons, okay? And the point is, every open set is a union of those kind of things in a base, and maybe one base is easier to use for one purpose, and another base is easier to use for another purpose. But it determines the same open sets there, okay? But now if you want to say, in general, we know those familiar examples, but what are the common properties of all those examples? In other words, they sometimes call axioms for point set topology. What are the common properties of having a neighborhood base or having just the family of open sets? I mean, it's perfectly good for some people to say, oh, don't tell me about bases. I just want to know what the open sets are, and that will be my topology, okay? So the thing is, what is common to all these examples that we're familiar with? And so in the case of the neighborhood base, is you have to be careful because you want the open sets to be closed under intersections. I mean, if you're approximating this and you're approximating that, it may turn out there's a common approximation and you want to see that as an open set. And so you have to be careful to make sure that finite intersections of things are there. So a neighborhood base is such that it will have that property. I can't read it from here.
Because why would a break do with infinite intersections?
Because infinite intersections of open balloons will be the closed balloon. Take all the balloons around the given balloon, and when you take the infinite intersection, you put the boundary of that kernel things in there, and that's what you don't want. So open sets are closed under finite intersections, arbitrary unions. And that's the reason.
All right, and just to be clear what we mean by closed there, because there's two different uses. One is closed.
Formation,
yeah.
Formations are allowed.
You can do as much unioning as you want and still have an open set. And you can do as much finite intersections as you want, and you'll still end up with open sets.
When you say arbitrary, you mean possibly infinite?
Yes, exactly. Yeah. Okay, more questions.
Sebastian?
Could you explicitly give an example of an infinite intersection such that you end up with a closed set?
Oh, sure. We essentially had it here. Take the closed interval between 0 and 1, okay? And think of all open intervals, rational open intervals, that contain it.
Okay, yeah.
And when you take everything outside,
And you intersect them all.
you'll have to put in those endpoints that will be closed there. Right? Yeah, so a lot of topology also has to do with thinking of inside, outside kinds of things, and which direction, I mean, especially in Euclidean spaces, where are you approximating something from? And maybe from one side to the other side. And so sometimes you have to distinguish those. But that answers your question, doesn't it? One thing we're trying to say here is these topological notions come into all kinds of things, and there are a lot of very familiar examples. And we want to look at one kind of super-duper topological space that contains lots of structure. But it's not a very amazing space. It looks like a trivial space at first, but then we'll show that it has some other properties. So Jeremy, carry on here.
Very good. Thank you. All right. So there's a few ideas. These are terms from topology that are going to come into play. And we've already been talking a little bit about, various Euclidean spaces that we were talking about just now. And maybe the most important one here is going to be continuity, which is we're going to be interested in functions and how those relate to the space that you're in. Okay, and so you've probably let's draw a little picture here about continuity. And you probably remember seeing pictures in calculus about functions like that And right, here's our x and our y. And you may remember something about epsilon and deltas, about what happens when a function is continuous, right? And it's saying that let's say I'm interested in f at x here, but maybe I can't measure exactly what's happening exactly at x, right? But I'm maybe plus or minus something, and let's say I want my answer within a certain sort of range. It's like at the end of the day, your client is saying, I need the answer within an error of plus or minus epsilon, okay? And so the question is, how good do I need to make my measurement such that I get within a certain range on the output, okay? And if what a continuous function says is, hey, there at least exists some delta. We don't know what it is, perhaps, but as long as there is a delta such that when we get within that delta, we're guaranteed to end up within epsilon, okay? And so this function has to be, continuous in order for that to happen. If instead my function had funny jumps in it, like let's say the function went to here and then jumped up to here, or something like that, jumped around, then I could be measuring over here and be getting a very wrong answer for something that really should be down there, for example.
Let's say it in neighborhood terminology here.
Yeah. So
Epsilon and delta, let's say it in terms of neighborhood.
right. So the epsilon delta, those were little intervals, right? And so the interval corresponds to a neighborhood. Okay. So now we can read this definition here, which is now in terms of neighborhoods. So a function between topological spaces is continuous if for every x in the space, right, and every neighborhood u, okay, so we've got our, neighborhood that we want to u that's around f of x, okay, so that's our epsilon, okay. Then there exists some neighborhood around x, right, some neighborhood v around x, such that when f of y is in u, then for all y, they're in v. Okay, so it's really we've just swapped out the notion of interval for this generic notion of, what's that?
For every neighborhood of f of x, there is a neighborhood of x.
Yep.
Such that for every y within that neighborhood, f of y is in the other one.
I dropped that for all part at the end. That's what he was emphasizing.
I'm nitpicking again.
Yes.
But at least written correctly, though.
Yes, that's correct. I trailed off and forgot to say the last part there. For all y in v. Yep.
Okay, I think that's good. I'm going to go to another bit of background on topology here.
Casey, do you mind, just really quickly, can you map that continuity thing to your little function? Because you're saying, given that there's that x delta, you can always draw a line.
The epsilons are giving a neighborhood of the function value, and you say no matter how you specify a neighborhood of the function value, you could have been close enough to the input to stay within that damn neighborhood, okay? That means you can't have a jump like you have here, because if you try to do it here and give a neighborhood around this place here, then if you choose an input over here, you jump out of that neighborhood. You can't approximate it there. So that's how you eliminate jumps out of the things. Of course, those are fairly simple-minded examples there, and the behavior of continuous functions can become pretty complicated. And of course, one of the things that often done in the calculus is continuity is a property of preserving limits. And here we're having just the very basic steps of limits of doing closeness one step at a time. But another way of looking at continuous functions is to say continuous functions preserve limits, and that contains the same thing. Now I want to pass on a little bit more here, some background. And this is partly a joke, because in the literature on point set topology, you see there are T0 spaces, T1 spaces, T2 spaces, T3 spaces, so forth. Now, the kind of space we're going to be looking at is a little bit more expansive than Euclidean spaces, and they're called T0 spacers. And Kolmogorov introduced them probably in the 20s, sometime, the famous Russian mathematician. And then as people looked at different kinds of spaces, they found other conditions about the behavior of neighborhoods. And so T2 is a very important thing because the real line is a T2 space. Actually, I think it was already defined by Wiener. Wiener went to study with Bertrand Russell. He was a teenager still, I think. He was very clever about it. But Hausdorff gets the credit for the axiom, unfortunately, there. And then as people started thinking also function spaces that we're not going to talk too much about, they realized that the neighborhoods had to behave in more and more specific things. So here is the joke. Well, let's just look at the definitions. T0 means each point is uniquely determined by its neighborhoods. An example of a topological space is to take a very large collection of points and say I only have 2 open sets today, empty and everything. Now that's really a stupid topological space because you're not making any distinctions between the points. But it satisfies the conditions there. So T0 eliminates that. T0 says that if you take 2 distinct points, they have to be distinguished by their neighborhoods. So one of them will have a neighborhood that doesn't contain the other. You don't know whether it's the right-hand one or the left-hand one, but one or the other of them can be separated from the one. And now T1 space is a little bit stronger. It says each pair of distinct points, you'll be sure for each of the pairs of distinct points, you can find a neighborhood of one that excludes the other one. A neighborhood of one that excludes the other one. However, what we're used to from geometry and calculus is the Hausdorff condition on the real line or in Euclidean space of there. 2 distinct points always have disjoint neighborhoods. That's a stronger condition, that you can separate things simultaneously around both points and make sure that they're not next to each other. So that's a stronger property.
That's T2.
Mm-hmm.
That's called T2. Now what does T stand for? You see in the beginning, Kolmogorov probably wrote in German. Many of the famous Polish mathematicians wrote in German. And so that period of point set topology was very often published in German. And these are called separation axioms, but they're not called S axioms, they're called T axioms because the word for separation in German is Trennung. So it's a Trennungsaxiom. That's why they call it T. And of course, people hardly ever explain that, and so it's really odd. Why would they use notation like that? Now here's the joke. As people worked in functional analysis and found more and more heavy-duty spaces, they had to get stronger and stronger properties of more separation. Not just separation between points, but separations between, say, 2 closed families of points or something like that. Stronger separation. So what did they come up with? They called them regular or normal or completely normal or perfectly normal. Mathematicians have no imagination in getting any terminology there. But you can look up at Wikipedia has quite a good article on it that gives background on those things if you're interested to see what it is. But the whole point is there, as you look at these subtle properties of other spaces, you need to have more and more possibilities of separation, not just the separation of points. One thing I should point out that is a PZero space is also a partially ordered set because you can say one X approximates in terms of neighborhoods another Y if every neighborhood of X is a neighborhood of Y. The approximation here is X has a certain number of neighborhoods and all of those are neighborhoods of Y, so that's nice for Y. But Y is a much fancier guy. He has many other neighborhoods that X doesn't, and he won't let X have any of them. You see that you can have stronger and stronger notions of closeness. Some points have a certain amount of closeness possible, but other points can have lots more closeness possible. And so you have that partial ordering relation. Does everyone understand what a partial ordering is? You know what a partial ordering is? Reflexive, transitive, antisymmetric. It means if X is less than or equal to Y and Y is less than or equal to X, then they're equal. And that's the T0 axiom, because if 2 points have the same neighborhoods, they have to be identical. So that means X less than or equal to Y and Y less than or equal to X implies X equals 1. Okay, and then another comment there. But now we're coming to the thing that we really want to make use of. And so, Jeremy, do you want to talk about the power set now?
Sure.
Okay.
Sure, I'd be happy to. Give you a little break again.
Please.
All right. Maybe some more board space.
By the way, what is the cardinality of the power set? What? 2 to the aleph naught. That was Cantor's famous theorem, right? The integer he called cardinality aleph naught, and he proves that the power set of the integers is not countable. And he went further to think about how you could do some things about arithmetic of cardinal numbers, and you can bring in some ideas of exponentiation. We won't talk about it just now, but then it turned out that the power set of the integers has the power 2 to aleph 0, and Cantor's theorem is those two cardinalities, aleph 0 and 2 to aleph 0, are different. And the long unsolved problem was, is there any cardinality strictly in between? And Paul Cohen showed that it was consistent to find models of set theory where there are intermediate cardinals, but you'd never meet them on the street. So don't worry about that.
All right, so what's going to happen here is going to be we're working up towards being able to talk about this other topological space that's about functions, okay? But before we get to that, so we're going to be, mathematically, a function is just a set of pairs, input-output mappings, right? So the notion of set is important there. And so this space here is going to be a big set of lots of sets, right? Each function is going to be a set. So we're first going to just start talking about sets, and then that'll build into functions, okay? And so we're going to put a topological space that's all about sets, okay? And so, right, how do you define a topology? You need to decide on a neighborhood, what your neighborhood's going to look like. And so what we're going to do is we're going to say that the neighborhoods are going to be finite sets, okay? And then what you want to think of that finite set as doing as giving you a partial description of lots of possibly infinite sets out there, okay? So let's do a very little concrete example. Suppose I wanted to just talk about the set of all even numbers, okay? So, the set of all n where n is even, right? So this is an infinite set, okay? And, maybe so here this was a cloud of functions. Maybe we'll also include any old sets in here too. We could have the set of all even numbers here, and that's one of these infinite sets. Well, how can we describe a finite approximation to this thing? Well, here's a set, 2, 4, 10. Okay? This is a finite set. Okay? And we're basically saying, okay, this finite description is going to sort of specify, describe a whole region. Let's call this set S here. S is going to sit here. Well, now S is going to be a region. This is the S region. And all the sets that include 2, 4, and 10 are going to be in this region. And you can have lots of other stuff in there too, right? Besides 2, 4, and 10, right? But as long as you have 2, 4, and 10, you belong in that neighborhood, that S neighborhood, okay? So the set of all even numbers is indeed in that neighborhood. You could have the set of like every other even number, that would be in there too, and so on.
Okay, let me give the people the exercises that are on this slide here. Okay? So who will solve the first exercise? Power set of n is our topological space. Neighborhoods are determined by specifying a finite approximation to a possible set, finite number of elements of the set. So I hope you have that neighborhood base in mind, and so we have those other definitions there. So now, how do you pass from a neighborhood base to the open sets? We discussed that a little bit. So let's apply that to what are the open subsets of power set of n, this topology. Who wants to?
What do they look like, just in general?
Okay, the points are sets. I'm waiting to get more of you in here. Did you have a question?
No, I said.
You want to give the answer, okay, but let's wait a minute. The points are sets. An open set is a family of sets. When is a family of set open in this topology? What's your answer?
Well, is it that you have all the integers plus or minus 1 non-inclusive?
No, you're thinking too specifically of particular sets. Okay? You have to think of those arbitrary sets as points. See, we have types here. They're the integers, they're the sets of integers, then they're the sets of integers. Okay? And so I'm asking you, when is a set of integers, set of sets of integers, open in this topology?
Is it the strict subset?
No.
How about a set of root to power n's in that? So like each set.
No, you don't have to worry about counting. You don't have to worry about counting things. No.
Any sets. Something like sets whose complement is infinite.
No.
Any union of the sets?
Ah.
Closed from the union?
What?
Any union of the sets?
Well, no. The union of two open sets is open. Okay. And the you have to be a little bit careful about the neighborhood base here because we're talking in terms of approximating a set from inside by its finite subsets, right? An infinite set is known more and more as you generate all the finite subsets of the infinite set, and we're thinking it that way. And so if a neighborhood means give a finite set for the neighborhood base, give a, I have to say this right, a finite set determines a basic neighborhood of all the sets containing that finite set. Okay, and so you have to be a little bit careful here in which way they do. What is the intersection of two neighborhoods? Suppose E0 is one finite set and E2 is another finite set. Each one of them determine a neighborhood. What is the intersection of those two neighborhoods? we think about intersections all the time in topology, especially with open intervals there. The intersection of two open intervals is another open interval, unless they happen to be disjoint, of course. And so, what is the intersection of two neighborhoods in power set of n, where the neighborhood base is determined by the finite subsets? Of the union.
Yeah.
Yeah.
You union those two finite sets.
Yeah. Intersection is defined logically by and, but if you say which things are such that E0 is contained in something and E1 is contained in something, it means the union of E0 and E1 is contained in something. So you have to be a little bit careful about your ands and ors in thinking of these things. But let's have another suggestion of what you think the open sets are going to be.
Is it the upward directed set at any point?
That comes in nicely there, but you can say something simpler.
Any set,
Because
any set containing any one point.
that's very close.
It's just the whole power set, the whole thing.
The whole power set is an open set, but we knew that was going to be there anyway.
But it's sort of like-
Set is an open set, and we knew that.
Arbitrary sets containing any single point. Is it sets placed on the unit?
Yeah.
Well, I mean, another way to phrase the question is, let's say I give you let's say there's a particular open set that you want to describe.
I think we need a picture.
Yeah,
Kind of
yeah.
hard to draw a picture.
How can you describe that open set in this basis?
The power set is a Boolean algebra, and so examples of Boolean algebra are very well known. There's the two-element Boolean algebra where you have false and true. Then you can have the four-element Boolean algebra, and you could consider that as empty set, singleton 0, singleton 1, and the whole thing is the set 0, 1, like that. And then you know how to draw pictures of, you've drawn pictures of Boolean algebras, right? You think of higher dimensional cubes, you know how to draw nice pictures of higher dimensional cubes. But what we really want to go is to the totally infinite dimension here. And the best I can do is just sort of lump it together here, is that there's the whole set is one point, and the empty set down here is another point. And then the points in between there, I drew a point there, but I'm thinking of a whole set of integers. When I put my finger on that point, you just can't see what it is there, but it's a whole set of integers. And so a neighborhood looks like this. A neighborhood looks like this. You take a finite set here, E, and you consider all the sets such that it contains a finite set. In other words, this is a finite amount of information about a possible set there, and so I say, well, which sets are appropriate for that finite set? That's all the supersets of the set, okay? And so that's one neighborhood base there. And now I could do another one here. Let's say call that E0. And then take E1 over here and take all the sets containing the second one. Okay, the union of two open sets is an open set, but that is enclosed under intersection, as someone suggested. Maybe you didn't say that, but someone suggested, well, no. You see, there's a bit of approximation here and a bit of approximation here. I could go on and do another one with a picture like that. That's just the union of three basic open sets. I didn't need to have the basic set closed under union. I needed to have the basic open sets to give approximations there. So what do you think is happening here if I took an arbitrary union of basic open sets I should be able to get the arbitrary open set. Let's go back to Euclidean space. In three-dimensional space, the neighborhood base are the open balloons, okay, the interiors of the sphere, okay? And in general, the open sets are unions of those, and you can fill up many strange shapes by little tiny spheres. Yes? So we're doing the same thing here. So what do you think? This is a very simple-minded open set that's just determined by three finite sets, but I could take many different finite sets and union them together. And so what is the characteristic property of a family of sets that way? It will be a union of basic open sets. What's the characteristic property?
It's just the natural numbers.
Whenever a set belongs, it should have been given that permission by means of a basic neighborhood. Whenever a set belongs, there's some basic neighborhood that says, okay, you can belong. Okay? You think of unions of these things here. If I think of these functions here, no matter what set I think of, there is a reason that it belonged, because E0 could be used. Well, E1 could have been used, but don't bother me about that. E0 was enough to put it in. But over here, you see I can only use E1. The way I don't draw these is rather separated here. On these areas here, you can only use the bottom finite set there. But you can imagine other configurations where some permitting things would be related to ways other things permit there, and so it can fill up the picture of the power set there in a fairly complicated way. But the characteristic property is a set is open if and only if every point has a neighborhood wholly contained within the set. If you think of a closed sphere, it's not open, because if you take a point on the boundary, there's no neighborhood that doesn't spill over to the complement. So a closed sphere is not open because of the boundary points being on the boundary between inside and outside. But what we're saying here is that an open set has to be such that a point belongs if and only if a whole neighborhood of that point is contained within the open set.
But there can be multiple.
It could be.
There could be multiple.
Yeah.
contained.
Yeah,
We just have to, there just has to be at least once.
Which is what we're showing there with the three different E1,
Yep.
E2.
Right, yeah. And then, like, kind of in this picture, if the open set is this square that we're trying to describe, this point is in the square. Why? Because there's this particular neighborhood, this circle here, that it was in. And if we can go through all the points in this square and find a little balloon that justified that one being in there.
So now we come to the functions that Jeremy wanted to get to. So to be a continuous function, I just go back to the basic textbook on point set topology and express the definition of continuity in terms of neighborhood-based elements. And so a function from the power set to the power set is continuous if, whenever you look at a point x and a finite set that gives a neighborhood of f of x, whenever you put a neighborhood around f of x, you could find a neighborhood of x that makes everything give that approximation E. And so I shortened this here a little bit here. A very key part of continuous functions, and it would follow from the way I logically wrote the definition, but let me not make you sweat over it here. A continuous function will always have the property that if x, no matter what x are, if x approximates y, then f of x will approximate f of y. Continuous functions on the power set with this neighborhood, because we're looking in terms of approximations about what is in, not approximations that are not in. It uses only positive information about the points. You could think of positive and negative information, but that's a different topological space. I'm only using positive information about what's actually in those points there. So it'll turn out that continuous functions have to be monotone there. And so what's an example of a monotone function? Monotone is a very simple-minded property. The more you put in, the more you get out. That's what monotone means. What's an example of a monotone function on the power set that is not continuous? Well, what?
The log function?
Couldn't hear.
The log function?
Oh, let's not be too complicated.
Well, and
Let's just think in terms of amounts of information, okay? And
remember, this is a function that takes a set and returns a set.
yeah.
Because we're
Yes, yeah. So, I want to have a function, and the way we usually write it in mathematics, I'm thinking of a function from power set of n
right. So
to
set
power set of n,
a set of naturals to a set of naturals.
which is monotone, but not continuous. There are a lot of trivial monotone functions. Every constant function is monotone. Oh, but constant functions are continuous. Constant functions in topology always turn out to be continuous. So what's a monotone function that is not continuous?
One that maps the empty set to the empty set and everything else to the full set.
Well, that's a good question here.
I think that's right.
The answer is f of x equals empty if x is empty, and f of x, what did you say, the whole set?
All the naturals,
All the naturals if x is
not empty.
not empty. Good question. Continuous or not continuous?
A continuous function is one where everything in the domain is an open set, right?
Say again?
Continuous functions applied to open sets return open sets.
It's the other direction.
Okay, so let's just test here.
Actually, no, I don't.
Think of any
no.
Maybe not.
You're close.
case,
You're
yeah.
close.
Think of any x and think of any neighborhood of f of x.
To add one more case.
Can we find a neighborhood of x where the values will be contained within that neighborhood? Well, there are two cases. X is either empty or not. So if x is empty, okay, and how do I want to say this? Oh, okay. Yeah, no, it's okay. I was confusing myself here. It's really easy. This is going to be continuous, so this is not the example we want to hear, because if x is empty, f of x is empty, so the only damn neighborhood you can get of it is empty, because that's the only finite approximation to empty. Okay? Now, is it true that there's a neighborhood of x? Is there a neighborhood of, well, what's the only neighborhood of x when x is empty?
Empty.
The whole space.
Or the whole space.
The whole space power set. The only neighborhood of the empty set is the power set of n itself, okay? Now, is it true that when you take any y in the power set of n, it will be the case that empty is contained in f of y? I take a neighborhood of x, and I say, does there exist a neighborhood of the empty set, which happens to be that crazy x, power set of n, such that for every set, it is true that f of x belongs to the neighborhood that I started with there. And of course, it's trivially true because the empty set is contained there. So we also, I'm getting a little bit tired here.
So this one's continuous.
Well, I just checked it at x. Now, if I take it,
I think if we swap out the empty set for any other specific subset, then
I think it will work out. I'm sorry, I'm getting tired, and that's why I'm.
If you want, I could switch to a simple variation of this that is definitely not continuous.
Okay, well, no, this is a
Or,
good example to say this is continuous, and we'll say it in a different way soon. The example I was looking at is that for being non-continuous is f of e is empty for every finite set e, okay, but f of x jumps up to n for x infinite. And the thing there is, and it's another exercise to prove, is that continuous functions in topological spaces, even those very abstract spaces, continuous functions have to preserve limits. And so, if you take an approximation going more and more up to try to reach a limit, and all the finite approximations are totally wimpy and don't get you anywhere, then it's not going to be the case that the limit of thinking of it that way, the limit of the finite approximations of x for f of x, for f of e, finite approximations, the limit will be equal to f of x. That won't be the case here because you said I needed finiteness to give me this kind of approximation, but when I took an infinite set x, I said, oh, make the answer n. And so I jumped from being empty to being full there without doing it in a smooth way that follows the way the approximations are supposed to go. So that will be, see, this is sort of different from this example here. So I have to check out the, I'm sorry, I'm getting awfully tired here, so let's think of where we are here and just try to make a little bit of a conclusion here.